Hi guys, BuildZoid here, and today we're going to be taking some oscilloscope measurements of the V-core regulation on the EVGA Z790 DARK. Basically, the idea behind these measurements is we want to find the LLC settings where our absolute minimum voltage is as close to the average voltage as possible, because the CPU's power consumption is dictated by its average voltage under load, and its stability is dictated by the minimum voltage. So we want these two to be as close together, because if there's a big gap between them, you are using a lot more power without gaining any extra stability. Anyway, let's get into it. So we're going to go into the setup. I just have a really garbage tier CPU overclock on here right now, just for convenience. Basically the idea behind these, don't copy these settings. These are not good settings. The point of these settings is that they're consistent. They work on every motherboard. I don't have to worry about them being unstable or anything. Even when we're on very aggressive LLCs, like, say, V-droop completely disabled. I gotta say, I do actually really like the way EVGA labels their LLC settings. So this is you have default, and then you have 25% droop reduction, 50% droop reduction, 75% droop reduction, and no V-droop whatsoever. So disabled is basically EVGA's equivalent of, say, Gigabyte's Ultra Extreme LLC, or Asus Level 8 LLC, or MSI Level 1 LLC. ASRock Level 1 LLC kinda also, but not... Well, it depends. ASRock motherboards are very inconsistent about what exactly Level 1 does, but... yeah, anyway, disabled basically means there's no V-droop under load, and our load voltage will actually be... Or, idle to load voltage will be static. Now, on the oscilloscope, we will not be seeing that, because the oscilloscope is measuring the core voltage behind the CPU socket, not at the actual silicon itself, because while it is doable to get those measurements, it's a massive pain, and I don't want to deal with it. So yeah, this isn't the... basically what I'm saying is this measurement setup that I have here is not perfect, but it's good enough. If there's major voltage regulation issues, we can very easily see them with this methodology. As for where on the motherboard I'm connected, it's as far away from the V-core VRM as possible, because the closer you are to the V-core VRM, the more... basically the more suppressed the voltage, the transients, get by the output filtering capacitance of the VRM. So anyway, yeah, we're going to start with disabled V-droop and 1.22 volts. And then we're going to go... we're going to increase the V-droop. We're going to test all the way down to plus 25%. I've already pre-tested the motherboard. There's really no reason to go... even default LLC actually does a very, very good job. So I'm not entirely... plus 25% has a very slight advantage. So that would be, worth experimenting with if you have voltage headroom. But if you don't, then default actually does an excellent job, as we will see. But we're going to start with disabled, just so you have some idea of what you definitely shouldn't do. Also, I have tested the VRM switching frequency. It doesn't do anything. It's pretty typical for motherboards, in my experience. Changing the switching frequency on the VRM on most motherboards achieves absolutely nothing. It does not improve voltage regulation. The idea behind adjusting the VRM switching frequency is that if the VRM has a faster switching frequency, you have more opportunities to adjust the current flowing through each phase. However, most modern digital voltage regulators, when they actually encounter a large transient, don't necessarily... they're not going to be in their sort of default, just switching each phase, interleaving all of the phases at a fixed frequency. They won't do that. They're going to actually start to overlap phases to get more current to the CPU, or they're going to start intentionally skipping PWM pulses to basically burn off the excess energy from the inductors in the body diode of the MOSFETs, though on some controllers that gets disabled because it can sometimes cause it. If I'm not mistaken, on some very old power stages and old motherboards, it would actually cause issues where the VRM would get damaged in the end. So that doesn't always get used, but depends on the VR, like the power stages and the voltage controller and how it's been programmed by the motherboard manufacturer. But generally speaking, on motherboards, changing the switching frequency does nothing. There was also some old motherboards where actually lowering the switching frequency would give you a voltage regulation improvement. There's been some relatively recent motherboards where maxing out the switching frequency would actually cause issues with the like load line calibration getting completely broken. On this board, I've not noticed any weirdness with changing the switching frequency. I tested all the way from 300 kilohertz up to 1,000 kilohertz. It makes no difference to voltage regulation. It also doesn't cause any issues. So, yeah. But I also didn't measure any improvement in voltage regulation. So there really, in my opinion, there's just no point adjusting the VRM switching frequency. I would just leave it at 500 and call it a day. Anyway, so let's actually go run some Y-Cruncher, what is it, small FFTs? 1.22 volts and disabled V-droop. Also, this board's voltage regulation is just insane. Like, I mean, it still doesn't manage to eliminate undershoot when you have literally no V-droop because there's just nothing that can be done about that. As you can see, we're already seeing the voltage occasionally dip down to 1.18 volts when the target voltage is 1.22. Yeah, if you look at the peak-to-peak value, so this right here, this is very, very low. I mean, right now we're at idle, but once we get under load, this still stays extremely low, which is kind of neat. It's not actually important, because the reason, so peak-to-peak is like a common measurement for like VR, like voltage regulation. I don't like it as a measurement. It's not a very good measurement. And the reason I don't like it as a measurement is because your peak to peak is your overshoot combined with your undershoot. Now, overshoot looks really bad and it looks scary, but under most circumstances, it's very rare that you'll have a motherboard where the overshoot is high enough to actually be dangerous to the CPU unless you're already at unless your average voltage is already so high that like that's already a concern. Though there are some motherboards, low-end motherboards, that are spectacularly bad, and there the overshoot will be a problem, but on those motherboards, the VRM will also regularly not be able to maintain sustained load, and they'll have like broken LLC settings. Like basically, the only time I've ever seen overshoot be high enough to be concerning is motherboards where they're so bad that you shouldn't be using those motherboards in general anyway, and the undershoot on those motherboards is also terrible, so it's just like everything is bad. But anyway, so overshoot is generally not something that I concern myself with because in most circumstances it just kind of looks ugly but doesn't really do anything, whereas undershoot is what causes the CPU to blue screen. Your peak-to-peak measurement is your overshoot combined with your undershoot. So the reason why peak-to-peak isn't that helpful is because it is very easy to crush overshoot with just extra capacitance. You don't really need amazing capacitors to deal with load release overshoot, like even through-hole polymers will do a very good job of that. And so consequently, it is very easy for a motherboard to basically have good overshoot handling, while the undershoot is terrible. But, you know, like, because peak-to-peak is a combination of the two values, if you have really good if you do a good job of suppressing overshoot and your undershoot is terrible, you still get like an okay peak to peak measurement, which is why I don't like peak to peak, because it's like I don't care about the overshoot. So this combined measurement is just like it's cool to look, like it's cool to see a motherboard where, as you will see, actually you won't really see it when we're on this aggressive LLC that we're on right now, but I mean, to be fair, like if I'm not touching the mouse, 80 millivolts peak to peak or 90 millivolts peak to peak, it is very impressive. Now, if I move the mouse around, we do get the mouse sort of stalling out the Y-Cruncher workload, which causes the voltage to just fall off a cliff. And that's sort of the main reason that you wouldn't want to use this level of LLC. Also, the very regular spikes that we're seeing in the waveform right now, this is just the Windows event timer. That's what the operating system uses basically to make sure that everything is ticking along correctly. If you're running like a video, the Windows event timer will actually crank up all the way to a 1000 hertz. In order to ensure like smooth video playback, that kind of thing. It's basically just used for like timing of events in the system. That's why it's called the event timer. Anyway, right now it's at the default, I think, 64 hertz, which is a really weird value. When I first came across the Windows Event Timer, like, what was really annoying was, like, I thought it was, like, interference from the monitor or something, right? Because it's really close to 60 hertz, but it's not 60. It's 64 hertz. So, yeah, that was fun. But eventually, like, I did figure, like, I think with Elmore's help, I managed to figure out that actually it's just the Windows Event Timer, and basically every like 64 times per second, Windows will basically check, well, hey, is everything running as it should? And when it does that, you get these big transients because if you have, well, actually you get them even at idle, right? You could see this behavior already at idle. But when you're running a heavy workload like Y-Cruncher, it basically interrupts the workload for a short period of time. And I'm just gonna, right? And so when it interrupts the workload, we go from pulling a very large amount of current, the voltage shoots up, so that's our load release overshoot, right? Because the load release is when the CPU stops pulling current, and pulling current is the sort of the wrong way to think about it. The CPU basically acts as like a low impedance resistor, but anyway. So we get this load release overshoot, and then once Y-Cruncher resumes, we get the voltage getting dragged down. And that would potentially, like, that can cause the CPU to crash, is like the bottom of this right here. Now, of course, we can make it significantly worse if I actually just move the mouse around. So we're going to move the trigger a bit. And there. Now, actually, the beginning of this isn't really a concern. So I'm going to try to recapture that better. There. So like this right here, so you can see sort of like, oh, the system registers some mouse input, and we get some load release overshoot, more load release overshoot. Then here, I believe this is just actually processing the mouse input. Maybe Y-Cruncher is still kind of running on some threads at the same time. But this right here, yeah, this is bad. this very much looks like Y-Cruncher just went to full speed, and the VRM just wasn't ready to react to it yet. And so we do get quite a lot of undershoot in that scenario, and that's almost certainly where it would crash if the overclock was like right on the edge of stability, which is it isn't, because again, I don't really feel like trying to take voltage regulation measurements with a system that randomly crashes if you touch the mouse. That doesn't make measuring things very easy. But anyway, so that's what's going on, and yes, in typical, motherboard fashion, like V-droop disabled is bad for voltage regulation. Like, it doesn't take a genius to figure that one out. So I'm going to move on to minus 25%, and I should have probably closed Y-Cruncher before trying to restart. Now I want to go fast through. Actually, we're trying minus 75% next. Misspoke. Like, it makes sense, because the way the V-droop is actually implemented is the VRM basically pretends that there is a certain amount of resistance between itself and the CPU. And there is a certain amount of resistance, right? Like, you have the impedance of the power plane, and the idea basically with load line is if you match the load line setting of the VRM to the impedance of the power plane, you don't get undershoot and overshoot, because the VRM isn't basically trying to fight the physical properties of the connection between itself and the CPU, as well as the inductors that make up the VRM, because those also cause issues. And probably the reason why this board gets such incredibly low peak to peak is that it has very low inductance inductors combined with just a ridiculous amount of output filtering. So yeah, anyway, we're going to go up to, oh man, this board has 3. I'm relatively certain that the voltage regulator on this motherboard does not support 1 millivolt adjustments, but I've not bothered to check. At least it shouldn't. Where is it? V-droop. So we're going to try minus 75%. But anyway, so the reason why it's like minus 75% for like the second smallest amount of V-droop that you can have, or like the minimum amount of V-droop you can have before having no V-droop, is because basically what the V-droop setting is doing is it takes the resistance that the VRM pretends exists between itself and the CPU, and we're reducing that resistance by 75%, right? So like the stock resistance might be like, pretend that there is 1 milliohm of resistance between the VRM and the CPU, which would mean at 100 amps we would see a 100 millivolt voltage reduction, right? So if you have idle at 1.3 volts, it's going to drop down to 1.2 volts on a 100 amp load. Now, if we reduce the V-droop by 50%, we're basically saying, okay, the resistance is now 0.5 ohms instead. 0.5 milliohms instead of 1 milliohm. And now you're going to get 50 millivolts of V-droop at 100 amps instead of 100 millivolts of V-droop at 100 amps. So yeah, I really like the naming convention that EVGA has for that. Like it's way less obscure than like the other. The thing is, on some motherboards, I'm not actually sure how exactly the LLC is implemented. On this board, or at least most digital voltage controllers will just allow you to have like a V-droop offset, like they'll have like a V-droop offset register or a trim register, I think it's called, where you can just adjust by a fixed percentage steps how much V-droop you have. And usually I think it's like 12.5%, 25%. I think it's in 12.5 percent increments or something. It depends on the VRM. Anyway, so that's minus 75%. We clear that, we can see that the undershoot when, I don't touch the mouse is better. The peak-to-peak value has improved very slightly. Of course, if I do move the mouse, yeah, things are still not great. But it's about 20 millivolts better now than it was with the what was it? Disabled V-droop. So, yeah, it's kind of that. And honestly, like, well, 20 for certain benchmarking scenarios, 25% or minus 75% might actually make sense. But for like daily usage, I wouldn't recommend it, mostly because the voltage regulation on like the default V-droop setting is so good. And it's not a lot of V-droop at default. Like there are motherboards out there where the like default amount of V-droop is way more than what this board has. So I'm guessing the stock load line on this motherboard is actually matched pretty well to its power plane, or yeah, which is kind of interesting because I have a suspicion that with a lot of other manufacturers, their power plane is just designed to match like the worst case scenario load line from Intel, which is why they need tons and tons of V-droop. But anyway, so yeah, minus 75%. It's a bit better than disabled, but it's still nothing particularly impressive. I mean, the peak-to-peak looks really good, but there's still undershoot, and it's not insignificant. So now we're going to go up to 1.29 volts. So the interesting thing is actually as we increase the amount of V-droop, these idle transients stop being like a combination of undershoot and overshoot, and it actually ends up being just V-droop downwards, because whenever the Windows event timer sort of checks what the system is doing, the CPU pulls a little bit of extra power to do that, right? So that's why, like, on the really aggressive LLC, right, you get a basically equal spike upwards and downwards on the just like Windows event timer at idle. But as you have more and more V-droop, that spike basically just goes downwards. It stops going up because there's no more overshoot anymore. Anyway, let's run Y Cruncher again. Clear the statistics. We're still averaging about 1.27 volts. If I don't touch the mouse, like right now, it basically looks like we almost don't have any undershoot. Almost. There's like 20 millivolts. Now if I move the mouse around, yeah. Not as much of an improvement compared to the, not... Actually, I think the voltage isn't quite matched. But But, you know, now we're getting minimums of like 1.22 volts with an average of 1.27 instead of minimums of like 1.2 with if I did my preparation correctly, it should have been close to 1.27 previously as well. Anyway, so next we're going to go down to minus 25%, which actually at that point, I think like this is what, like, I think in benchmarking scenarios, minus 25% actually ends up being very viable, because if you're not intentionally spazzing out the mouse, your workload will basically only get interrupted by the Windows event timer. Oh man, I missed it. This board boots too quickly. But yeah, if you're not spazzing, like if you're not intentionally spazzing out the mouse during a benchmark, you won't have that really big like mouse related, like mouse processing transient. So in benchmarking scenarios, the minus 25% actually probably is very viable. Even minus 50% might be. But like minus 50, we were still getting like measurable undershoot. Like I could still trigger on it if I wanted to. So I'd say that's not that impressive yet. Okay, so next up, 1.325 volts. So yeah, now we can basically, like, we can almost not see the overshoot from the Windows event timer anymore. Right? And now let's try Y-Cruncher. Oh, there we go. Yeah, so the voltage is still around 1.27 volts on average, right? We're at 1.269, so I did my best to try match them up in pre-testing, but I can't trigger off the undershoot anymore. Not no, yeah, not really. I can trigger off the overshoot. If I move the mouse, yeah, it's not having a good day. But if you don't touch the mouse, so if you were running like Cinebench or something, right? Yeah, this LLC would actually do a very good job. And Cinebench is actually a lot less difficult on the VRM than Y-Cruncher is. Like this is a pretty extreme workload. Where's my trigger at? So I would like to. Oops. Then there we go. So yeah, that's the mouse input again. Yeah, so we do get like mouse interrupts Y-Cruncher, overshoot from the mouse interrupting Y-Cruncher, then Windows doing Windows things. I'm assuming Y-Cruncher is still actually kind of running during this. Actually, maybe it's just mouse processing. I'm not sure. Like, unfortunately, I can't look at exactly what instructions the CPU was running at this point in time. And then here we have the load insertion undershoot right here. So, you know, yeah, if you touch the mouse, then minus 25% is still not ideal. But for like just straight up benchmarking, I think minus 25% is actually very, very viable. Because when the benchmark itself is running, there's minimal undershoot. Oops, there. Did I accidentally pause Y-Cruncher somehow? Oh no, it's just... I did something. Yeah, I think I accidentally paused it. Anyway. Let's try default LLC. And on default, like, it does a very, very good job. Which I gotta say, like, that's actually really cool from, like, a overclocking perspective, is, like, you don't actually have to change the LLC set. That's what I get for holding the delete button instead of mashing it. Like, holding the delete button just doesn't work. It just doesn't. No, but I do think it's really cool that, like, you can just use the default LLC on this board. Like, you don't have to change it. On a lot of other motherboards, the default LLC, like, well, so on some motherboard, yeah, no, on some motherboards, when you, like, well, ASRock motherboards mainly do this, is when you manually change the core voltage, they'll automatically give you an LLC setting. That's just completely stupid. You've got to be kidding me. But with, say, Gigabyte motherboards, the, like, standard LLC is unnecessarily droopy. Asus boards, I'm not sure what they default to off the top of my head right now. I think it depends which specific Asus board you have. Yeah, whereas Gigabyte motherboards, well, their AMD motherboards aren't. It depends. Really depends. Unfortunately, it's not that consistent. Well, part of the issue, especially with AMD motherboards, is that AMD has just a completely different approach to their voltage regulation configuration, like the VRM settings. Oh, wait, I forgot to change the LLC. I'm so stupid. Oh, well. I'm sure Windows won't be upset by me interrupting its ability to boot up. Yeah, we want to go back to default, and we're at 1.365. Oh, it did get upset. But you can reset out of automatic repair as well. Okay, let's hit Y Cruncher. Hello? There we go. A little bit high on the average voltage. We're about, 3 millivolts above 1.27, but not the end of the world. And yeah, at this point, there's no undershoot, and if I move the mouse, there's a little bit, but it's like 1.248. So what, like 25 millivolts? Which is pretty much as good as it gets. Okay, it's a bit more than 25 if I keep doing it. So like 30-ish, which is still extremely good. So yeah, the default LLC on this board is like dialed. It's not necessarily completely perfect, but it's very close. I guess it's a tad more aggressive than what you would see on some other motherboards, but then again, you also have the options to increase the V-droop. So I'd say in terms of performance, it's kind of similar, I guess, to medium on Gigabyte boards, or like level 5 on Asus. Yeah, I think level 5 on Asus. Like high-end Asus motherboards, because low-end Asus motherboards have different voltage controllers that behave differently from the high-end Asus motherboards. Which, to be fair, that's like pretty typical of most manufacturers, that they don't use the same VRM controllers across their entire lineup, and so the LLC behavior can be kind of different board to board. Anyway, anything more than 25% is not necessary. So, anyway, I'll wait for Windows to actually like do whatever it is that's like showing up on the oscilloscope right now before starting Y-Cruncher. Okay. Hey, there we go. Yeah, I was just trying to start it too quickly. And evidently I overshot it on the voltage a bit. We're like 5 millivolts above what ideally I would have wanted to be at. Yeah, now if I move the mouse, we're getting 1.26 volts minimums with like a 1.277 average, which is what, like 17 millivolts of undershoot? That like that's insane. Like this is in the range of like my old oscilloscope would not be able to measure this. Like, yeah, like this is the main reason I wanted this scope, is just like, yes, so much accuracy. But that's the thing, is like 17 millivolts versus like, what was it? Previously we had like 25-ish. It's not really going to significantly affect your like overclocking results. So yeah, I think the default LLC on this board is honestly like, unless you have a CPU, unless you have a very cooling limited setup, I think the default LLC on this board does a great job. Yeah, I can't really see a reason to like if you're gonna if you're benchmarking like Cinebench or something, you might want to bump it up to like minus 25%. Maybe I don't like minus 50. Just straight up say like minus 50, the undershoot is like very noticeable even if you don't touch the mouse. So I'm gonna say minus 50 is actually bad, but minus 25%, like yeah, if you're not intentionally spazzing the mouse out, like I don't see a reason that like Cinebench would crash mid-load or something like that. It really shouldn't, especially because Cinebench compared to Y-Cruncher is basically a joke. Actually, let's try that. Let's see what Cinebench looks like. Yeah. 50 millivolts peak to peak. It's like idle, basically. Oh boy. Yeah, so if you're running like Cinebench, then like minus 25% or something, right? Because obviously if you do move the mouse, then yes, it will interrupt the workload, but like you don't move the mouse when running a benchmark, because like that's like the thing, right? Like when you're pushing a benchmark full out, like like you can even see on the oscilloscope that the mouse is evidently getting in the way of the CPU's ability to run Cinebench. Right, so if you were spazzing the mouse out during your Cinebench run, like it would probably score worse by a potentially significant margin, depending on how much you spaz the mouse out for how long. But yeah, like, so just like the voltage regulation on this board is extremely good. For daily overclocking, quite frankly, I would just leave it on the default LLC, and I wouldn't go from that, because even the default LLC, like, it's not that droopy. If you compare it to, like, say, standard LLC on a gigabyte board, like, uh, there's more V-droop on that. Like, way more V-droop on standard. Well, admittedly, I haven't checked the Tachyon Z790 yet, but the Z790 AORS Elite that I tested, yeah, like standard LLC. I didn't even use standard LLC in the video because there's so much V-droop that you need to idle at like over 1.5 volts to get a reasonable load voltage. And there's I've not checked every motherboard yet, but like there are more examples of motherboards like that where like the maximum amount of V-droop, which admittedly this board does that too, right? If you go all the way to plus 90% V-droop, you'd probably end up like in order to reach the load voltage that I'm getting here, you'd probably have to be at like 1.6 volts or something, which is stupid. There's no reason to do that. Like, yeah, but well, actually, maybe if you were messing around with dynamic overclocking, the crazy high V-droop settings would be interesting if you wanted like a static voltage setting, but then wanted to use like V-droop to do all of the dynamic voltage scaling based on how much like core load you have. Which that would be like the main reason to use the higher V-droop settings that this board has available, is if you wanted like high voltage in like single to quad core loads, which actually quad core load it's not actually low load. Most of the power consumption of a 13900K is the P cores. So half of so 4 of the P cores being at 100% load is actually kind of a lot of load. So yeah, that wouldn't actually, but you get the idea. So if you wanted like a high voltage for your low core count loads, and then a lower voltage for your high core count loads, you could maybe benefit from like plus 50%, plus 75, something like that. But even then, I don't think you'd actually want to use that. I think, well, plus 75, I think would be really unusable. Like, because at plus 25, we're already at what, like 1.405 volts for idle. Yeah, I don't really see much reason to go outside of the range of like LLCs that we've tested here. Well, I mean, to be fair, I don't really understand why you'd ever want to use V-droop disabled, because that just sends voltage, like that makes the voltage regulation bad on basically any motherboard, and this one's no exception. To be fair, the peak to peak is still very impressive, but the undershoot is still really bad. Right, like that's like the thing is just like when you disable the V-droop, there's your undershoot is just kind of like, well, it's just kind of there, and you can't really do anything about it. Because you simply cannot get enough capacitors at the CPU to be able to have disabled load line. Like, that's just not a thing. Like, that's the whole reason load line even exists. Is just the limitations of power delivery. Just say no, you can't just. I mean, to be fair, see, like NVIDIA's solution to the whole, like, well, you need like a DC load line if you don't want any undershoot, is like, well, what if you just stretch the clocks anytime the voltage isn't high enough? But Intel CPUs, I think now they actually can do that, but it's not like Intel's default intended behavior. I almost feel like Intel has it more as like as a precaution for like exceptionally terrible motherboards, rather than like, oh, this should actually be something the CPU is taking advantage of regularly. But anyway, yeah, so the Z790 DARK, the default LLC settings on this board are actually very good, and you kind of don't need to, like, yeah, if you're doing just daily overclocking, there's no reason to change the switching frequency, because that actually does nothing. We're not going to go into how it does nothing, because don't feel like doing it. Like, the video's long enough as is. And then the default LLC just does a very good job. Potentially, if you're cooling limited, you might see a benefit by going to plus 25%, but other than that, like, yeah, no, the voltage regulation on this board is just, like, out of the box, is just very, very good. And I'm really a big fan of the fact that, like, the default LLC is just, like, a good LLC. Like, there's just no reason to, there's not really any major reason to change it. which is kind of neat because on most other motherboards, yeah, the default LLC either is ridiculously droopy or on some motherboards just kind of bad. Well, actually, usually on motherboards where the default LLC is just kind of bad, any LLC setting is also just kind of bad. But yeah, no, like this, like I'm impressed. It's not really surprising considering the hardware that this motherboard has in its power delivery, but it's a good result. Like, yeah, and I am still impressed. And I'd be lying if I said I wasn't impressed by the peak-to-peak number. I am, but at the same time, I acknowledge that this is a dumb measurement that doesn't really tell you the full... Like, it's not a very useful measurement, because it tells you, like, half the story, right? Again, the undershoot, way more important than peak-to-peak. But anyway, that's it for this video. Hopefully this was somewhat helpful. Yeah, that's it. So thank you for watching, and... like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. If you'd like to check that out, there's a link to that down in the description below as well. And that's it for the video, so thank you for watching, and goodbye.